Swayam Prabha. Digital India. Educated India.
So we take a system of particles which are not rigidly connected, and then after that we graduate to rigid body. Okay, so in the last class we did the minimum thing. So just to recall, so these are number of particles. So in this, there is one thing which required here is the center of mass, which so we define this one because this concept is very important. We keep using it repeatedly. And here, so if the particles have mass here, so the position vector G as this how we take the moment of the mass. Okay, so Ri times mass about the origin, and then we divide by the total mass view Rg. This is very important for us. So it can even be extended velocity here, and of course acceleration. So this sum total of all the velocities weighted with mass can even be written like this one. These concepts are important. For example, one, this is about the center of mass. This is about say the momentum. The linear momentum of all the particles is equal to the total multiplied by the velocity of g. So this is how we can combine. So similarly, the acceleration. And so now we have the center of mass. So now let's apply the Newton's law for all the particles. So we applying so for each particle here. So what we have here is that so this is I've done to some extent. So, but just to recapitulate, I can apply it to ith particle. So ith particle is acted upon by force F and Fij. So this is what is Fij? Fij is anything. It can be attraction, it can be repulsion, it can be any force between the particles. So the only thing we are saying, applying it to our solids or even fluids, is that this internal force is equal and opposite of the particles. So this is basically, this is external force and force. So if you sum it up over all the particles, so what we have here is that sigma Fi plus Fij this is what it is. So, but if you look at the Fij here, since these forces, internal forces occur in pair, okay, so this Fij acts, Fij and Fji are equal to each other in magnitude and they cancel. Fij so if they occur in pairs and if they cancel, so that leaves only the and this Mi times Ai is, if you look at the definition of the center of mass, so Mi times Ai is nothing but the total times A. This is a very important observation here. That means that when there are forces acting together with the internal forces get cancelled, leaving the total forces, all the external forces combined together will be equal to, by simply the mass and total mass of all the particles multiplied by acceleration of the center of mass. Okay, so this is a very important and observation, that this Fij get cancelled. Okay, so after that, so we can continue this one. The other important thing is that obviously you can see that this is a vector equation, and that vector equation will give you 3 scalar equations. So you can find out the position of mass, but it doesn't give you distribution of the various particles as the motion takes place. So if tomorrow, if we go to the rigid body, so we know that how the center of mass is moving, but we do not know the orientation. So to determine the orientation of rigid body or the system of particles is, we have to look at how the moment of the forces and affect the mass time acceleration about some point. So that we call now as angular momentum. So we have to bring in angular momentum about some point, or this is also is simply moment of linear momentum. About some point. So both are equivalent. So now what we mean, so the momentum of the linear momentum of ith particle Gi is the linear momentum. is, if you write it as GI, this is how the linear momentum, and to take moment of momentum, this moment is obviously about some point here. Let us say, to start with, let us O. So say here about O. So then the momentum is nothing but the cross product. So the cross product is, we call it as using H. Is nothing but so there's a lot of this derivation keep on going, because this is an important part of it, because this will tell us the orientation of the system of particles about G or even body later. So this is how we define the moment of momentum. So this is Ri cross MIVI. So that we call it as HI. Of course, also had to put the subscript O here. And so the total angular momentum about, say, O is nothing but HO is nothing but summation of so this is how we define this is the total angular momentum about, say, O. So put the subscript O here and H. Okay. And like this, we can simplify this also, of course. And we can define this momentum not only about O, there are many other points of interest. Other points of interest are other points of interest. So we can even write down the angular momentum about G, for example. So we call it as Hg. So Hg, but say if you have a G here, so if you have so we have to the G. So if this is Ri, and this vector is nothing but Ri minus Rg, which we call as quotient vector of I with relative to G. So this is Ri minus Rj. You can see very well it's equal to Ri, J. So this is what we write here. So everything else, only this position, this relative position vector that changes. Earlier it was the Ri directly to the origin, whereas here this is Ri slash G. So this is about H, and this is linear momentum about G. There's also another definition of this angular momentum is the second here, this is the first, and the third one is the linear momentum. Here we take the linear momentum relative to so what I mean by this? So that means that this Hg here, we call it as relative, and so here the linear momentum, we write it as so you are seeing various differences. So here this is the absolute velocity, whereas this is Vi with respect to the velocity of ith particle with respect to g. So what is this? So here Vig is nothing but right. So this is how another quantity Hg is defined. There are a few other definitions also. For example, you can take any other point. So any other point say P here, and which is represented by Rp with respect to the so the definition of with respect to P is exactly follows that of with respect to G, except that is it is an arbitrary point. So here this is the fourth one. So HP is exactly like this. Only thing is that so what is that here? So this is the absolute velocity, and whereas this moment about which you are taking is with respect to P. So RIP here is nothing but of ith particle with respect to P, right? So this is P, and there's one more of interest is relative. So you can guess what this is. So in the relative, it is still the moment about so there are so many possibilities are there, and here the relative angular momentum of all the particles about P is here we take the relative velocity, and obviously this position vector is with respect to P. There are various possibilities which we use, depends upon our convenience, and we understand all of them. Some of them G is much more useful. We'll see one by one. We'll see one by one. Let us just. So let's look at the angular momentum, the first one, for example. Let's look at this one. Let's take this again. So this is momentum which involves velocity. So if we want to relate it to the forces which are acting, then we have to differentiate these bonds and then see how the terms appear. Okay, so differentiating it time. So what we get is what ddt of HO is nothing but ddt of this one. So we have, let's do this. Okay, so we have two terms, the position vector Ri as well as velocity. And if they are functions of time, so we have to take the time derivative of those terms. Okay, so here this dr by dt is nothing but velocity. And in this one here, AR, right? There is a summation for both. Okay, so you can very well see that the first term drops out, this Vi cross Vi. So this is, and this leaves here Mi AI. So this is Mi AI can be equated to force acting on the particle, right? So we know that this can be written as Fi, not only Fi, this is the external force, but the Fij also happens to be force acting on the ith particle. So that as far as the ith particle is concerned, we have to take Fij, both we have to take. So this is external force and this is the internal force, which becomes external force for ith particle. So how do we, now we have two terms. So can we show that the second term here, Ri, consider this Ri Fij. So this occurs, so this occur in pairs. But this Ji, but Fji acting on jth particle. That so this is the jth particle and this is the ith particle. So this Fij and Fij, Fij is acting on the ith particle and Fj is acting on the jth particle. So we show that the total contribution is 0. So this is because we are Rj and they are different, right? So here this is Ri and this is Rj. So how we show it is that we know that Fji is minus Fij, right? Of times Fij minus Rj times Fji becomes Fij. You can show that so can we show that this is 0? Rj, it is nothing but Rj is nothing but a vector in this direction. So this vector so this vector here starting from jth particle, that is, and what about Fij? So Fij is also acting along the line. So this minus Rj, which on this one, this Fij are also directed along the same direction. So these directions are or same. So if they are same, then their contribution is 0. Right? That way, so if you come back here, then we can say that Ri cross Fi. So this is, I'll just write it down in a nutshell here. Again, so this is one important equation which says that time rate of change of angular momentum, which is taken about O, is equal to what is this Ri cross Fi? So that is nothing but moment of all the forces about O. So this is nothing but the moment of all external forces about O, right? So this is a very important observation. This is about what is O? The origin, a fixed origin a fixed point, and it's the origin. This might even turn out to be same result when we talked about the fourth and fifth definition about a point, right? So some of them, when it's fixed point, then it will turn out to be same. Okay. So this is about angular moment, about O. So then actually the second and third definitions are very important for us. Okay, so let's look at the HG. So consider HG, which is given as so if you take, because we want to relate it moments acting, so that means that we have to take it to the acceleration. So we'll take a derivative. Derivative with time. So what we get here is GG dot. And here we have RIG dot to start with MIVR plus in fact, I can, now that you know it, then I'll just replace it by AI. So this is nothing but very clearly RIG times, put it the external. Now we know that the internal forces moments contribute to 0. So this is nothing but, what is this? This is nothing but the moment of all the forces about. So can we show this first term to be? So this, consider the first term is so how to show that this contribution is 0? So we can write it interestingly. This VI we write it as velocity of G right? So the first one, Vg is common to all. So what we can do is that, let's just say, I'll just take it, I can still retain it inside. Right? And plus yeah. So what do you think of this one? So the first term in this Vg is common, so we can take it out. So that turns out to be that's that. The first term is Rig dot. Sorry, there's something which I missed. There's a dot missing here. Yeah. Yeah, there's a dot missing here. Yeah. So then again here, there's Ig. There's a summation for the second. So what do you think of this one? So this is Mi, velocity of G. So in the definition of center of mass, we have defined this is nothing but velocity Vig is going to be what? Mi Vig is going to be, how is that Vig cross? Exactly. This is very clear. Oh, that's what about this one, Vig, V cross? So if you look at the definition of center of mass, can you look at first one with respect to G? So with respect to G, if you recall, Mi Rig is 0. See that? This is how we defined it by definition. Right? So if you do that, so one differentiation, right? Find the center of mass. G about G is 0. So similarly, the velocity is also 0. So differentiation. So this becomes 0 and totally it's 0. Plus what we have here, we said that this is equal to M. So what we have here, so if you take the momentum about G, and then if you differentiate it, then that should be just about G. So this is another very important observation. So I'll quickly go through the other I think we can go on doing it. Just one last one, just want to derive is, yeah, one last one is about Hg. I want to prove Hg is the same as J. Okay, so that means that either we take H or JL is all same. So let us just do whatever we can say for about Hg, we'll also say about okay. So what we have that the same thing like we is a manipulation of this thing. So this we can write it as Pg right. So the first term will, for example, the first term we can write it as minus Pg cross is the first term. Just interchange. I brought Vg out. Okay, so it's very clear now that, sorry, please. This we know to be 0, right? And that leaves only this part, which is nothing but, this is Ri MiG is nothing but so that's Hg is equal to Hg rel. So the other two is to quote it without proof because you can do that regarding about P. Okay, momentum. We defined it I'll just quote the results. You can prove just like these manipulations, G about P and so on manipulating. So what we have, HP can be related to Hg. Just take them. So regarding about any other point, P, so it can be related to Hg. Just a lot of manipulations are there. There's nothing. So while differentiating with time, we get P and finally we have So these two are in fact, this is about any point P. This is about any point P, that both the definition. So if you take time derivatives, so this is what you get. So the moment of all the forces about P is the rate of change of angular momentum, relative momentum with time, and then RGP cross MAP. Okay, so think this later often, but for this one, the other things can be derived. For example, if P itself is G, if P itself is G, okay, if P is G, what happens? Then RGP will be 0 and simply becomes HP relative, right? And P is origin, RGP again, this. And we have and relative, okay. And so similarly, there's also one more occasion where simply becomes MP is equal to HP rel when RGP is parallel to AP. So on 3 occasions, so this MP will become HP rel, and G itself is P itself is G, or P is origin, or RGP is parallel to AP, right? So this is so please go through these things, try to arrive at just a matter of algebra, a lot of manipulation, but we'll be using some of these, this, that one, okay, H4 dot, HG dot, going to use.